All right, test equipment. Most of the test equipment, well, a lot of the test equipment now has become digital, where back in my day, it was analog. Like oscilloscopes. We have spectrum analyzers, antenna analyzers, or vector network analyzers, kind of the same thing. Oscilloscopes, talk a little about doing RF measurements and some computer-aided measurements. So first we'll talk oscilloscopes. We used to just call them scopes. Like I said, back in my day, they were all analog. It was either a Tektronix or an HP. Not too many other people made.
And they were heavy.
Yeah, big, heavy. The big Tektronix that I used, you had to have it on a cart. It was just like 1.5 feet wide and 2 or 3 feet tall. Either 2 or 4 channel. In fact, those big Tektronix had a lot of plug-in modules for the vertical and horizontal, and even logic analyzer, all kinds of specialized plugins, so they could do a lot of stuff. In the newer ones, they've all kind of gone to digital. And it's kind of like when we talked about SDR radios, it's the same deal. You're using an analog to digital converter. So the sample rate is going to determine what the highest frequency is that you can see with it. And also the reference level just into the AD is going to determine the highest signal that you can see reliably. So which of the following limits the highest frequency signal that can be accurately displayed on a digital oscilloscope?
Alpha.
Hey.
Alpha.
Hey,
Now, it says you have to know how to use the digital scope properly, even though it does have some advantages over the analog. This one really surprised me, and I haven't actually gone and tried to see if that's really true, but this implies that if you change the horizontal time base on a digital scope, that it reduces the sampling rate. Now, I never thought about it before, and I didn't think that's the way it worked, but it's possible, and it's doing, when we talked about the A to D stuff, doing decimation, where it's dropping samples. So that's the only thing I could think of is how you could get aliasing, because the only way you can do aliasing is you're sampling at less than twice the frequency of the signal you're trying to look at. So if all that's true, it means when you lower the time base, it's lowering the sample rate. Definitely not the way an analog scope works.
that way.
I didn't either. And that's, I guess, they're pointing out why it's different on a digital than an analog. And I hadn't had time to really verify if that's true with this one.
If you lowered the sleep rate, you ran out of memory. Because that's maybe
At the high, if you had the high sample rate, yes.
Because you only have so much space to put. If you're doing 1 million samples per second and you're doing a 3-second sweep, you're gonna end up only part of the screen, or it has to reduce the sampling rate.
Oh, yeah. But today, storing 3 million samples is a piece of cake.
2 gigabytes, 5 gigabytes are now
Terabytes.
terabytes even.
Okay, so what's the effect of aliasing on digital oscilloscope caused by setting the time base too slow?
Alpha.
And I guess if they are doing decimation, then if you remember from when we talked about that, you need an anti-aliasing filter.
Yeah,
Probes.
yeah,
That was a question.
I remember.
Making measurements at RF frequencies. You need to make sure that you connect the scope probe as close as possible, or the ground on the scope probe, which is usually right at the tip with a very short lead. In fact, we used to have some that actually had a little, almost like a pin that you could connect to ground, so it was right next to the tip of the probe. To prevent any noise pickup, because that little, at high frequencies, that little 1 inch or 2 inch length of ground lead is a little bit of an antenna. I mean, it could actually be a quarter wavelength for really high frequency stuff. In fact, you get up high enough frequency, you can't use a regular probe anyway. So keeping the ground connection as short as possible. It also reduces the inductance of the ground connection. So you get a more accurate measurement. Which of the following is good practice when using an oscilloscope probe? Keep the signal down.
Alpha.
Alpha, sure. Oscilloscope probes. Good quality, passive, because there are some active probes. We'll have a adjustable capacitor. And for people not familiar, we have anybody who's never used an oscilloscope probe? Wow. If you look at the connection on the back where it plugs into the scope, the BNC, you'll see there's in that module, there's a little adjustment hole. That's where that capacitor is.
Oh, okay.
And you adjust that for compensating for the input impedance on the scope to match it to the probe. It's kind of like matching to an antenna. And they provide, I guess I've never seen one that didn't. You see over here, this two little outputs, one's ground and one is I think it's a 1 kilohertz square wave.
Okay.
And you use that to adjust the probe. You connect it to that, and then you adjust that little trimmer capacitor in there to get essentially a perfect square wave.
And it's calibrated at that point.
That's, you consider that calibrated.
So the calibration adjustment is actually part of the scope. It's not part of the probe.
No, it's part of the probe. It's the
Calibrate the probe to the scope.
BNC, and they're almost always a BNC connector on the end of the scope probe
Right?
is usually in a little module, and it has a place where you can adjust that trimmer capacitor.
Oh, so there's
Now-
a little rectangular box right there just before the
Yeah.
BNC and the
Now, I
probe comes out of
remember
it.
having some where you could actually, it had a rotating adjustment
That's what I thought I remembered.
close to the probe tip. It did the
Yep.
same thing, but you compensated it that way instead of needing a screwdriver.
Okay.
There's an example of what you might see when you put the test pattern on the probe. So if you're undercompensated, you're going to see the top waveform. So you're getting extra harmonics in there. If you're overcompensated, you get rounding. And when you have it, quote, perfect, it looks like a nice, perfect square wave. Now, they came up with stuff there about being greater than 9 times the reactance of what the scope, I don't know about that. That didn't make sense to me. Because you can definitely go too far, which is what the middle line shows.
Well, I know back in the '70s, it cost about $150 for a good probe.
Oh, yeah, they weren't cheap. They're still, even though you can get Chinese on Amazon, they're still 30, 40 bucks for halfway decent.
$70 then was a little bit more than $70 now.
Yeah.
Yeah.
But you get a digital scope like that. I think I got it for about 250 bucks.
They're about 2,500.
Yeah.
And 1/10 the quality of that.
Okay, how's the compensation of an oscilloscope probe typically adjusted?
Alpha.
Yep. Okay, spectrum analyzers. Oscilloscope just displays the amplitude of the signal versus time. A spectrum analyzer displays the amplitude of a signal versus frequency. So one's time domain, one's frequency domain. And it's the horizontal axis that's different. The scope is time based. The spectrum analyzer, it's a frequency or oscillator signal. It's actually a sweep oscillator. And you set it up to vary from frequency X to frequency Y. In both cases, vertical will be the amplitude of the signal. The main thing that I've used as far as you can look for harmonics and spurious signals on a signal, like the output of your transmitter, or even stuff you're seeing on your antenna, which could be other noise sources around, and you're seeing it as spikes somewhere on the spectrum. And that's why they call it a spectrum analyzer, because it looks at a frequency spectrum of range of frequencies. This is showing simple what you would see on the oscilloscope and what you might see with that same signal on the spectrum analyzer. And you see the fundamental frequency there in the middle, and then a couple sidebands, assuming that was some modulated waveform. So which of the following parameters does a spectrum analyzer display on the vertical and horizontal axes?
Bravo.
That big.
Which of the following test instruments is used to display spurious signals and/or intermodulation distortion products generated by a single sideband transmitter?
Bravo.
Okay, antenna analyzers. And I guess these are more generically called vector network analyzers, but they sell a lot of them as antenna analyzers, which don't do as much all of the things that a real vector network analyzer can do. Basically, if it's just an antenna analyzer, like one of the Rig Expert, MFJ ones, and Comet makes one, I think several other people. They basically show SWR, and they can also show the impedance, the real and reactive components of it. Smith chart. Some of them can do a Smith chart.
Velocity.
The basic
Velocity.
difference with the analyzer, as opposed to using some kind of SWR bridge, is the analyzer has a built-in RF generator or source. So you don't need an external source to use it. It's part of the unit. And that's how it works. It generates a signal and looks at the reflection coming back. Oh, and I guess that next one there is you don't need to hook up your transmitter. If you're using an SWR bridge, you've got to have the transmitter going through the bridge to the antenna to see what the SWR is. If you're doing the network analyzer, you connect it directly to the antenna, and then you can actually tune the antenna by, you know, changing the length of the elements or some other matching mechanism. Let's see, what else? Make related measurements, the resonant frequency, and also the feed point impedance. And it'll usually show you a plot of the feed point impedance versus frequency. And that's also where you can see the resonant frequency. There'll be a peak or a null, depending on how you're looking at things. And you
the
can
price of one of these. Oh, is one of these how expensive one of these devices? I mean, is it affordable?
Antenna analyzer or
Antenna analyzer.
VNAs, those nano VNAs are like less than 200, right?
this was $90.
Then the rig experts are
Yeah.
around 300
And up.
Yeah, they're
Yeah.
made in Ukraine, so
The right.
A
But-
little more expensive now.
Yeah, Comet makes some MFG. I don't know who makes MFJs, but they have one. It's fairly popular.
but you can see the SWR over a range of frequencies. You
Yeah,
can see a bell curve or
but this is kind of the more popular thing. You get them for under $100. And it does
Which one is that one?
an H4. It's not the fancy one that Bruce got.
Oh, no.
He got one with end connectors on it, and a bigger display.
Do you, both of these are yours?
Yeah.
Okay, so I see Tiny SA and Nano VNA. Do you have any experience with the Mini 13?
No,
Okay,
I've only used those two. And I haven't used this much,
right.
but
now won't you spend quite a bit on cables?
Oh, yeah.
not too bad. You need adapters. Which is why you have one of those SMA to a PL 259, or you can get the same thing for an end connector. So you can connect directly to either one.
You can,
And it comes with a couple short SMA leads, and they're what, 8 inches long, maybe?
on Amazon, you can also find a package of all the basic connectors interfacing to some different things that cost like about $10 and you get about 30 different
Yeah.
connectors. They're not the best connectors in the world.
No, but you're only gonna use them
Once or twice.
And you showed that board last week.
Yeah,
the little
all right.
nano VNA board that has,
Well, it's
Sure.
actually, this was
Sure.
from Amazon. I think it was like $10. And it came with a couple adapter cables. And it's got, it's called an RF demo kit. And you actually calibrate. It's got short, open, and load on it.
that's worth its weight in gold right there.
And a through. It's got attenuators. It's got a low pass, a high pass, a band pass, a band BSF. It's a notch filter. What's SBSF? Band suppression filter.
It could be,
And it's got a couple SWR, a 33 and a 75 ohm. So you can look at all the stuff on the Smith chart, and then it's got a bunch of reactive series and parallel tune circuits. So you can
Really?
kind of do all the,
it's already built.
yeah. I wouldn't want to build that. They're getting a little too small for me. I've done some almost that size, but boy, it's a pain.
I can hardly see it, let alone doing it.
Well, you gotta have a magnifier. There's a picture of one of the typical nano VNAs. And you can see the two ports, channel 0 and channel 1. And we'll talk about those a little bit, where in this one, it's showing where you do an S21 or an S11, which are called scattering parameters or S parameters. So which of the following measures SWR? Which of the following is an advantage of using an antenna analyzer compared to an SWR bridge to measure antenna SWR? You didn't bring your SDR meter, did you?
Bravo.
They don't need us
I didn't
for
think
external
much.
source.
How should an antenna analyzer be connected when measuring antenna resonance and feed point impedance?
Delta.
Directly to the connector.
Okay. Frequency counters.
There's one thing,
Yes?
when you're measuring an antenna with an analyzer,
Uh-huh.
closer you get to your antenna, the better off you are. Instead of a long feed line, that way you get the true resonance of the antenna.
Right. And a better SWR because of loss in the line. It's
Yeah, because you get,
SWR at the antenna is worse than it is.
right, because you get, when you have a long feed line, right, that minimizes the effect of the antenna. It's long enough, you don't need an antenna.
You're just going to use like a small patch cable.
Yeah,
Yeah.
close to the
Or
antenna.
go up on the roof and hook it up.
No,
I use a shorter patch.
you drop it down, if your antenna's up 25 feet, go straight down and do it there.
Right.
That's the
Because
best.
if you lower the antenna
Don't
to
bring
do
it
it,
to the ground.
it's gonna affect the reading.
Yeah.
That affects.
It's the
resonant
Heisenberg
frequency.
principle.
Yeah,
That's-
Okay,
That's very true. When I put on a longer length cable, the SWR is
goes down.
totally different.
yeah,
It's perfect.
put 100, 200 feet on and got a really good
You don't have a
SWR.
care in the world.
Losses throughout the line.
You heat up the transmission line.
That's
Okay.
also the advantage of having an analyzer, you can go close to the antenna.
You're not pushing much power through it.
Hmm?
You're not pushing any power through it.
Right, 10 milliwatts.
Yeah.
And also you can analyze multiple frequencies at once sometimes.
Right.
You don't.
We can
you're
do a
not
whole
just-
band, yeah.
Yeah,
Now, that's one of the things on the nano VNA. They may have improved it on the newer models, but it's limited to doing 102 points. So the wider the frequency band you want to look at, the less accurate it is because you get a fixed number of samples. So if you really want a good reading, I mean, you look at a narrow range and then, you change it to do a different range. And you can actually store different calibrations. I think you can store 5. So you could calibrate it for, say, 4 or 5 different frequency ranges, and then you wouldn't have to.
yeah, the rig expert gives me SWR at 5 different amateur bands at once.
Yeah. And it costs multiple times as much.
350. I think it's 350.
Okay, so frequency counters. And it's just that. It's a digital counter that basically looks at the crossover of the signal and counts how many times it changes direction. If you're trying to measure some frequency above the maximum frequency of the frequency counter, you can add what they call a prescaler. And sometimes they'll have that built in. It reduces the accuracy, but it lets you operate at higher frequencies. So it's going to divide the incoming frequency before it gets to the frequency counter. So all you're really doing is dividing it, and then you multiply the frequency counter display by whatever the prescaler is. So you didn't gain any accuracy or resolution, but you can measure over a wider range. There's a typical cheap, probably made in China one. But they all look pretty much the same. And they'll have different ways to set up the ranges. This one looks like it's got some kind of recording feature. I'm sure the newer ones with all the digital stuff do all kinds of fancy things besides just measure frequency. So what's the purpose of the prescaler function on a frequency counter?
It's delta.
Okay, logic analyzers. They allow you to look at multiple signals at the same time in the time domain and display them so you can actually see different stages of a logic circuit and how things are working. They're, I'd say, invaluable if you're actually designing digital logic.
I usually have like 8 to 16 inputs at one time.
Kind of like that.
Yep.
And you can set markers on them and measure distances and offsets between them. And in some cases, you might even be able to measure the rise time and fall time of those signals, which sometimes is important. Which of the following displays multiple digital signal states simultaneously?
Delta.
And they have them relatively cheap as a USB plug-in for a laptop or a PC. I've got an old one. I think it was less than $100. And it does like 8 channels.